So I'll not try to convince you why lithium is important, but I will maybe try to convince you that we have a real supply risk in the next years, probably in 5 years or a bit more. So why we have this supply risk? Not because lithium is a rare metal, not at all, but because we don't have the good methods to extract it. So nowadays we have lithium coming from different sources. We in CMET have been working with 3 different sources that are the main source now in the world. So lithium from brine, that I will talk more today, lithium from clays or rocks, and also lithium from spent batteries. As you can see, the concentration of lithium in solutions can vary between 0.2 gram liters to 35 gram liters, and always in high water dependent process. So let's talk about brines. These brines came almost all from the same region in the world, known as lithium triangle, that's between Argentina, Bolivia, and Chile. And what are these brines? Are salty water, 10 times more salty than seawater, that contain lithium, but majorly contains also sodium, potassium, magnesium, calcium, boron, sulfates, and chlorides. How they are extracted, the lithium from these brines? The answer is pretty simple and pretty sad in the same time. They use solar evaporation. So what you see here in this photo is the Salar de Olaroz. So it's one of the biggest salars in Argentina. They just pump this in some ponds, and the sun can do the effect of evaporate all the water and concentrate the solutions. If we explain a bit better, so they start with raw salar brines. They go to evaporation ponds where the sun can make the job. After that, we have base addition where sulfates and magnesium are removed. After that, we go to a second evaporation pond when we have just 10% of all the water left. Then we have an acidification, solvent addition to have the boron removal, followed by base addition, and then extraction of calcium and magnesium, a polishing step, followed by then extra fresh water addition, sodium carbonate addition to have finally lithium precipitation. So just for the evaporation, we need 23 months of sun, is why we have this supply risk. We cannot make lithium from yesterday to today. We also have 50% of all the lithium that's lost. And basically, if we summarize, this is a process that do 3 things. So brine concentration, changes in pH, and a source of carbonate to have lithium carbonate. So what we've thought is, can we do this with a more simplified process where we would recover the water? And then we decided to try to use membrane electrolysis for that. Why membrane electrolysis? Because membrane electrolysis, as you can recognize, can do pH change, because we have water reduction to increase the pH and water oxidation to decrease the pH. Can do concentrations, because once the ions migrates the membrane, also water migrates with, and also can be controlled by the potential and charge that we apply. So the only thing that still remains, we need a source of carbonates. And then we say, why not couple this membrane electrolysis with a crystallizer where CO2 can be added, and then we can have the sodium or the lithium carbonate precipitation. So how we did that? So what you see here is the composition of a raw brine. So first step that we used was always an ion exchange to have the boron removed, and also an addition of a basis that in our case is sodium carbonate, produced as a byproduct that can do the bivalent extraction, calcium and magnesium. So the solution free of calcium and magnesium can go to the electrochemical cell. Then we have tested several processes where electrochemical cell is used, and after followed by precipitations. The different orders are used, but the best process was proved to be the process 2, where we have a direct use of electrochemical cell, increasing pH, additions of CO2, lithium precipitation as carbonate, and then just an extra addition of CO2 and the precipitation of sodium bicarbonate. So, how does this work? We have used a membrane electrolysis cell where we use an anion exchange membrane. Brine free of magnesium, calcium, boron is added in the catalyte, and then we have the anions that cross, mainly chloride, and with this we have also water crossing. So what we have been controlled is the volume change, as you can see in the graph, as the charge increase with the different current densities that we have been using. You have lithium and sodium that increase in concentration, and also the hydroxides. So we have migrate 35% of all the liquids, and we stopped the membrane electrolysis because we arrived to a concentration of sodium close to 7 molar. So we need to stop to have just lithium precipitation and not sodium. And in the same time, we have a lithium concentration close to 0.3. All the tests were done with 100 ampere per square meter and also 250. And the final concentration of hydroxides also presented. So we took this solution, highly concentrated in hydroxides and also in lithium and sodium, and we have flushed CO2 until we achieve a pH 11. And also we keep the temperature at 88 degrees in our crystallizer, because important information is that lithium carbonate is one of the salts that decrease solubility with increased temperature, opposite for sodium. So what we had result as crystallization is that we were able to crystallize 74% of all the lithium present in the brine, and this achieving a purity of 98.5%. What is pretty good. However, we have close to 80 kilowatts hour for each kilo of lithium carbonate. So if we take in consideration the price of energy in Argentina, we are talking about 3.58 euros of just energy for the membrane electrolysis for each kilogram of lithium carbonate that can be precipitated. Just to compare, the price of lithium carbonate nowadays is close to 8 euros for each kilogram of lithium carbonate. So can we have a byproduct that also can add some value to our process? Then what we do is with the remaining liquid that now has 0.07 moles liter of lithium and 7 moles of sodium, we have add extra CO2 until we achieve a pH of 8.5, now in room temperature this time. And then we can precipitate close to 30% of all the sodium that's present in the solution. And in this time, we have a purity that's higher than 9.99. This is the fact that we almost don't have other ions present. This means that our byproduct will be produced more than our product itself. So we can produce 1.9 kilograms of sodium bicarbonate that after drying becomes sodium carbonate for each kilogram of lithium carbonate that's produced. And that can also be used for the precipitation of magnesium and calcium. So finally, we saw that the best process that we can do with the membrane electrolysis is the process where we start with the solar brines as raw they are, without losing any water. We have the extraction of boron and the calcium magnesium. And after we use the electrochemical cell to do the pH change, and we have lithium precipitation followed by sodium precipitation. So we were able to do a new process based on membrane electrolysis, where that's controllable and weather independent. So we can do this in 2 days and not in 23 months. There is no water lost and no chemical addition except of the CO2 for the lithium precipitation. We can also extract some byproducts that can be also sold, and but we still have a really energy costly process. So the next steps and possible collaborations that we see is that we should test different membranes, because as you see, we are using an anion exchange membrane in a process that has chlorine evolution, so still not resistant for a long time. And also we are looking for the use and development of selective electrodes for the lithium that remain in the solution. We still have 26% of the lithium that stays. And also, we would like to test the same process in other lithium streams. Thank you, and I will be happy to answer if you have questions.